probability, chapter 5. This is section 1, an introduction to probability. So, what is probability? What are your ideas of what probability is? Other than reading the definition. Yeah. The likelihood that something would happen. It's exactly right. We run into it all the time. What are some of the examples in our daily life in which we run into probability? What are the chances that you get into an accident? Okay, what's the probability that you'll drive home today and get into an accident, or fly to Miami for a vacation this summer and you get in an accident? What else? Shout them right out. The chances of winning the lottery, right? What are those probabilities, right? So get a lottery ticket. Are you going to win? You're going to lose, right? Or gambling on a sporting event, or going to Las Vegas and playing blackjack, right? Or just simply flipping a coin, rolling a die. Any kind of example like that involves probability in our daily lives. Probability, the more official definition is, probability is a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. That portion of the definition perhaps is not as clear right now. We'll see an example in a second that I think will make that sound a little bit more. It'll explain what that means a little bit better, I think. But there is some sort of a situation, we call an experiment, where there is short-term uncertainty as to the outcomes of that particular experiment. So probability deals with experiments that yield short-term results or outcomes, yet reveal long-term predictability. In the short run, there is uncertainty, but in the long run, there is some level of predictability. For instance, if I flip a coin one time, is it going to be heads? Is it going to be tails? Right? That's short term. It's unpredictable in the short term. If I flip it 4, 5, or 6 times, that's still a short number of times. I'm not really sure what's going to happen. Maybe if I flip it 10 times, maybe all 10 times are heads, or maybe half are heads, or we're not really sure. However, if I do it, say, 1,000,000 times, if I flip a coin 1,000,000 times and it's a fair coin, one side is heads, one side is tails, and it's well balanced, so it kind of lands on one side or the other an equal number of times, and I flip it in a way that guarantees randomness. It's not some sort of a cute little flip where I'm always just getting the same result every time. So in a case like that, then if I flip it 1,000,000 times, then the long-term predictability makes me think that about 500,000 times it'll be heads, and about 500,000 times it'll be tails. So there's long-term predictability, even if in the short run we're not really sure what's going to happen, right? If one couple has a baby, is it a boy? Is it a girl? I don't know. There could be anything, right? But looking at the entire United States, all the couples having babies, I'm pretty confident about half of them are boys and about half of them are girls, right? There's long-term predictability, right? So the search for that long-term predictability is what statistics is about, even though we acknowledge that there is short-term uncertainty. Good? Questions, comments, issues? No? Las Vegas bets on that all the time. I bet one hand, $10 on one hand. I either win or I lose. There is short-term unpredictability for me as a player, because I'm only playing one time, and I might win, I might lose. Casinos don't look at that. They focus on thousands and thousands and tens of thousands of people that play hands every day of every year, every day, every minute. And so they're looking at the large numbers. They don't focus on one hand, one player, won or lost. Who cares? In the long run, they know that in the long run they're going to win, right? They have it set up. They know what proportion of the times they're going to win. They can apply statistics and have fairly accurate predictions of how much money they're going to win in the next year or two or whatever, right? Long-term predictability. Good. Okay. So the long-term proportion in which certain outcome is observed is the probability of that outcome. So the law of large numbers, I'm sure you've heard that many times before. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So that's the technical definition of the law of large numbers. But I'm not sure if that really clicks in yet, right? As the number of repetitions of a probability experiment increase, the proportion. Okay, so if we have a fair coin, a balanced coin, one side is heads, one side is tails, and we flip it, then what do you suppose is the probability of getting a heads? Just out of sort of gut instinct, we haven't really studied anything in detail, but probability that you flip a fair coin, flip it, and what's the probability that you get heads? 1/2 or 50%, right? 0.50, which is equal to 50%. All that stuff is good. Okay, let's look at this.
Okay, let's take a look at this little app. What this little app will do is it'll flip a coin for us, and then it'll keep track of the number of times that a coin flip resulted in a heads, and it'll also keep track of the number of times we flipped the coin. So for instance, let's push this little button here, and it flips a coin, and there we go, we got a heads out of that coin flip. It also keeps track of the number of times we received coins and the total number of coin flips that we've gotten. Okay, so we flip it again, and it'll keep a running total. So now we've flipped it twice, and both times we got a heads. Okay, so let me reset this. So the purpose of this little app is to keep a running total of the number of times we flip a coin and a count of how many times we got a heads during those flips. And what we're going to do is divide those to get a proportion of times that we've gotten heads once we've flipped coins. So let's start over. Let's say we flip a coin. Ooh, I got a tails. Flip it again. Ooh, I got 2 tails. Flip it again. I finally got a heads. Okay, so now let's take a look at this over here. What this is a running count of the proportions that are resulting as we flip the coin. So at this point right here, we can see that we got 0 heads with 1 flip. So therefore, the probability of getting heads is 0 at that point. At this point, we flipped it twice, and we got 0 heads with 2 flips. So still, the probability of getting heads was still 0. Then finally, we got 1 head. So at this point, we got 1 head when we had flipped it 3 times. So the probability of getting heads is 0.33 at this point, 1 out of 3. Okay, so then we keep flipping. Okay, finally, there we go. So we got 2 tails, 2 heads. We flipped it 4 times. Twice we got heads, and twice we got tails. So at this point, the running probability of getting heads with 4 flips is equal to 50%. Now, that's exactly what we know the answer should be when we have a fair coin. In a fair coin, we know that the probability of getting heads should be 50%, right? 50-50, there's 2 options, either heads or tails. If it's a nice fair coin and we flip it, there should be a 50% chance of getting heads. However, that's not the point of this applet. The point of this applet is to pretend we don't know the answer. So even though we know the answer is 50%, we're going to pretend we don't know it and see what happens. So if we don't know that this green line represents the 50% mark, which represents the theoretical probability, the probability of getting heads that we know should be accurate, then what we do is we just keep going. So as you saw, with just 2 flips, that was really far away from 50%. Even at 3 flips, it wasn't that close. It really finally at 4 flips, it was exactly at 50. But if you didn't know the answer was 50, then you might keep going. And then you would be off. Now with 5 flips, you would be at 3 heads and 5 flips. So at 60%, proportion of heads is 60%. And you would flip it again. and oh, you're back to 50%. But again, you don't know the answer is 50%, so you would just be in the dark, just flipping coins, flipping it again, and flipping it again, and flipping it again. Okay, back to 50%, but you keep going, back to 50%, you keep going. And now you're slowly venturing off away from 50%. Okay, so this is what is referred to as the short-term uncertainty. With just a few coin flips, there's a lot of variability because with one coin flip, it could be heads, it could be tails, there's uncertainty in the short term. The law of large numbers was telling us that over the long run, when I do this many times, that this will always eventually get close to the green line, the actual probability of getting a heads. So now I'm going to jump over to this button that will simulate flipping coins 1,000 times. So now we've flipped it 1,000 times, and we see that out of 1,015 total coin flips, 499 resulted in heads. When I divide this number by that number, I get 0.4916, which is really close to 50%. The green line. So as you can see, this blue line dances up and down, above and below, but eventually it gets close, really close to 50%, and we would just keep going. That's what the law of large numbers is telling us, that as we flip the coins many thousands and thousands and thousands of times, we get infinitely close to the real theoretical probability. In this case, we know it should be 50%. Notice that we hardly ever actually get to the exact 50%, but we get really close. We can get arbitrarily close. The larger the number of flips, see right now I'm at 35,000, 36,000, 37,000. The more I flip the coins, the closer I will get to the actual answer. So to recap, flipping the coin once, a lot of uncertainty. Could be tails, could be heads. Flipping it 4 times. Okay, look, I flipped it 4 times and there was only 1 heads. If I was just going based on this, I would say that the probability of getting a heads is only 1 out of 4, 25%. But as I do this thousands and thousands and thousands of times, right, the blue line will go up and above the green line and below the green line and dance all around it, but eventually it will get close to the desired, the theoretical amount of 50%, right? As we continue to flip coins more and more, 9,000, 10,000 times, 12,000, 13,000. As we do that, the proportion of heads gets closer and closer to 50%, which is what we know is the answer, right? And again, in a situation where we know the answer, it seems a little silly that we're doing this since we know the answer should be 50%, but the point is that in many cases we don't really know what the real answer is, so we're just left with repeating the experiment over and over again, thousands of times, and seeing where does it converge to, where does it get infinitely close to, and then we assume that that's what the theoretical probability is, you know, in cases where we don't know what the real answer is. Okay, so in the long term, there is predictability. It will approach the theoretical probability, whereas in the short term, there is uncertainty. Right? Let's go back to this. I flipped it 4 times, and this time I got 3 heads out of 4. So now I'm thinking it's 75%. Right? So short-term uncertainty, long-term predictability. Law of large numbers. This time with a different coin. So let's say that this is kind of a trick coin, a coin that is designed to only land on heads 20% of the time instead of the 50% of the time that we assume to be true. Okay, so but this is unbeknownst to you. So you start flipping the coin to try and figure out what that probability is. So you flip it, and you get a tails. Okay, 1. The running total at this point is 0 out of 1, So your probability, the proportion of heads at this point is 0. Okay, so then you keep going, and you get a tails again. So the proportion at this point is 0 out of 2, so 0. Finally get your first heads. So at this point, if you were going to stop right now and use this information to try and guess what the proportion of heads is going to be coming from this coin, well, the information you have would let you know that it is 1 out of 3. The proportion of heads is 33%. 0.33 is the proportion of heads with this coin flip. So you do it one more time, and now with 4, you get 1 out of 4. So again, short-term uncertainty, could be heads, could be tails. There's a lot of uncertainty in the short run, but in the long run, now if I start flipping these thousands and thousands of times, you see that at this point, with 1,004 coin flips, 193 of them resulted in heads, and the rest resulted in tails. If I divide 193 divided by 1,004, we get this proportion of 0.1922. And so as you can see, as we started flipping coins, the proportion of heads started dancing above and below the green line. But as we do more and more of these, this blue line, the running proportion of heads, gets infinitely close to the result of 0.2, which is the proportion that this coin is intended to produce. Okay, so if we keep flipping it, we see we get infinitely close to 20%. Right? So the law of large numbers, again, in the long run, with many trials, many flippings, here we have 24,000, 25,000 flips. We're getting really close, infinitely close to the 20% that this should be. Okay, so that's the law of large numbers, and the way we use it is in situations where we don't know that the answer was supposed to be 20%. You might come into this thinking that this is a regular kind of coin where it should be 50%. So that's your initial thought, that it should be 50%. But you do a bunch of flippings here, you keep flipping and flipping and flipping, and you notice that you get you don't get heads at a ratio of 50%. It seems to be closer to 20%. The other key thing is that we don't necessarily get exactly 20% here. We get close to it, infinitely close. And remember, if we don't really know that the answer is 20%, we won't know whether we're on the answer or not. We just got to rely on the knowledge that as we do this thousands and thousands of times, the law of large numbers dictates that this will get infinitely close to the real proportion, 20% in this case.
Okay, so in probability, an experiment is any process that can be repeated in which the results are uncertain, like flipping a coin, rolling a die. We need a little bit of notation. The sample space S, so we usually use the capital S, of a probability experiment is the collection of all possible outcomes of that experiment. So for example, if the experiment is we're going to flip a coin, the possible outcomes are tails or heads. If we roll a 6-sided die, then the possible outcomes are the number 1 or the number 2 or the number 3 or the number 4 or the number 5 or the number 6 come out. Right? Those are the possible outcomes when a 6-sided die is rolled. When we have a baby and we want to see the gender, then male or female, those are the 2 possible outcomes. When we call a random person and ask them how many people live in your household, right? Possible answers are 1, I live by myself. 2, 3, 4, 5, right? Those are the possible answers you can get. Okay? So when you can write down all the possible outcomes from an experiment, then that collection is called the sample space, S. Good? All right. Now, from the sample space, we think of events. So an event is any collection of outcomes from the probability experiment. An event may consist of one outcome or more than one outcome. When it's just one outcome, we call it a simple event. And we usually use the letter E in lowercase and subscript it to identify those simple events. And when it's a compound event, then we use typically a capital letter and either subscripted or maybe even multiple letters to represent it. So let me show you an example of this to describe these definitions. So let's say that the experiment is to roll one 6-sided die. And record the outcome. Okay? So our sample space S is going to be that the die was a number 1, the die was the number 2, the die was the number 3, the die was the number 4, the die was the number 5, or the die was the number 6. Right, that's our sample space. Okay, well, you could describe it this way, and in some word problems, the way to describe it is to do a picture, right? But in this case, it also makes sense to just write down the numbers. So in this notation, this represents that I rolled the number 1, the number 2, the number 3, the number 4, the number 5, or the number 6. So that's our sample space. Okay. So now events. Events come in 2 flavors. Events are either going to be simple events or compound events. So simple events are events that are one outcome, only one unique outcome from our sample space. And usually we use the letters lowercase e with a little subscript to identify them. So in this case, simple events could be, for example, E sub 1 is defined as you rolled the number 1. That's a simple event. Or maybe you rolled the number 2, or the number 3, or the number 4, or the number 5, or the number 6. Those are all the simple events that you could have. Okay? So notation, well, we could use this kind of picture, or we can use this, or we can also describe our sample space as E1, E2, E3, E4, E5, and E6, where each of these lowercase e's is described this way. Good? Questions? Comments, issues? No? No? Okay. Okay. A compound event is an event that's made up of more than one of those outcomes, of more than one of those simple events. So, for example, compound event could be we rolled one 6-sided die and we got an even number. We rolled an even number. We rolled an even number can be described by lots of different situations. Maybe we got a 2 or a 4 or a 6. There are 3 different ways in which we can roll this and we got an even number, right? You think of Las Vegas, there's some sort of a betting thing, and you're just putting money down that whatever the dealer rolls, it's going to be an even number. So whether the dealer rolls a 2 or a 4 or a 6, that makes you a winner. If you roll a 1, a 3, or a 5, then you lose. Okay, so the event even, we usually use capital letters. So maybe capital E to represent that it's an event. And so this one is made up of 2 or 4 or 6, that way. We can also write it down as E sub 2, E sub 4, and E sub 6. Okay. Or we can have another compound event. The other compound event could be that it's a perfect square. It's a number such that if you take the square root of it, it's a nice whole number, right? A perfect square. Perfect square. That's my event. I'm a math nerd. I went up there and I put 10 bucks on a perfect square. What? What is that? Okay, now we use capital letters to represent compound events. Now, in our book, I believe they use different letters. In some books, they like to do these subscript things, where they do something like this. This is E sub 1, this is E sub 2. They're different. You just got to pay attention to those numbers. But I believe in our book, they just like to go to a different letter. So for us, we'll just have a different letter. Maybe because it's a perfect square. Now the only thing is we don't want to use S, because S always represents the sample space. So that one's been retired. We don't use the capital S. But we can use, say, capital A. Okay. Capital A is perfect square. So of these numbers, which one of these numbers have a perfect, are a perfect square? Right? So the square root of 4 is 2 and 1. 1 and 4. Good. Questions? Comments? No? Okay, so I can write it that way, or I can also say that this compound event is E1 and E4. Any questions about that so far? No? No? No, we only use the lowercase ones when we're talking about simple events. And simple events, we always use the letter E for event, E. So the capital ones are always compound events that are made up of a combination of the little simple events. Okay? So it's one trial. That's the thing that people always get confused about. It's one roll of the dice. So even though we have multiple things in here, you can make up lots of compound events out of one simple roll, right? We can make up all kinds of things. It's a result, it's a number such that if you add them, the sum is less than 5. You can do a number that's bigger than 4. So there's all kinds of descriptions that you would come up with to describe a compound event. Or you might not even need an actual verbal description. You might just say event K is equal to rolling and you get a number 2 or you get a number 5. There's no it's not an even or an odd. There's no perfect way of describing them. You just said these are the two things that make up event K. Questions? Any questions? So we are clear on what is an experiment, a sample space, and we have events. So they're both events. It's just that some of them are called simple events and some of them are called compound events. They're both events. Good? And compound events are made up of all those simple events. Simple events come together to make up the compound events. Good? Questions? Good. Okay. So here's another example. Consider the probability experiment of having 2 children. Okay, so you have 2 kids. So you have 2 children. And we're gonna have a couple have 2 children, one at a time, and we're gonna record their gender. So boy versus girl, we're going to stick to just those 2 gender identifications. So boy, girl, 2 kids, 1 couple, 1 kid at a time. We're also ignoring the possibility that you have triplets or something. So if we keep track of their gender, let's identify the probability, the sample space of this experiment. So the experiment is that a couple is going to have 2 children, 1 at a time. We're going to keep track of their gender. So the first child is either a boy or a girl, and then from that we do this, it's called a tree diagram that will help us identify all the possible outcomes. So if we follow this tree across, we see boy, 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 this one leads to boy, girl, this one leads to girl, boy, and this one leads to girl, girl. Okay? So there are 4 possible outcomes that can happen when this experiment is, when we do this experiment. Is that clear? So, is it clear that these 2 things are 2 separate situations? This, boy, girl, and girl, boy, are treated as 2 different things, right? Because here the boy is older, right? So it is different than in this case, here the girl is older. Here we don't have to think about flipping them, because here the girl is older, right? And if we flipped it, the girl would be older. Okay. Since we're just keeping track of gender, there is no difference in flipping them. Now, that's one of the things that makes statistics hard. That's not a rule that's consistent always. There might be some other word problem out there where you do have to think about flipping them because they're different. So you have to ask yourself in every situation, does it make sense to consider the other direction? Are they going to be different just based on what we're keeping track of? Is it going to be noticeable if we do one versus the other? So that's something that we have to keep in mind. Okay, good, good. So there's our sample space. Our sample space consists of all four of these things. S is equal to, so this is one outcome, BB. Another outcome is BG. Another outcome is GB. And the last outcome is GG. One letter by itself is not an outcome. You can't have just B by itself. Right? You can't have that because the experiment was to have two children. The experiment was not to have one child, it was to have two children. So this doesn't make sense by itself. A possible outcome of the experiment is going to result with two genders. I mean, two babies, and each one has their own gender. Good? Yeah. Well, now you're going back to describing what the experiment is, right? So first you have to describe what the experiment is, and based on the experiment, then you have to think about what possible outcomes are. For instance, let's say I invent a game, and my invention of my game is you run out and find one person, and you, figure out whether they're boy or girl, and then you come back in here and you roll a die, and you write down one six-sided die, and you write down what you got, and then you go to McDonald's and you figure out the next customer in the drive-thru, how much money did they spend? Okay, so that's three things. Gender of one randomly selected person out in the hallway. You roll a die and you get something, 1 through 6, right? It's a six-sided die. And then you run over to McDonald's and you find out how much money that the next person that goes through the drive-thru, how much did they spend? Okay, so one experiment result would be those three things together, right? Because that's the experiment, those three things together. You can't just have one of them separately. Does that answer your question? Okay, so we have to think about what the experiment is and what the possible results of the experiment are. Now, if it had said, we're going to have a couple have 6 children, then one result would be a combination of 6 genders. Boy, 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 girl, 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 boy, 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 girl, right? So we'd have to think about all those combinations that are possible if they're having 6 children, if that's the experiment. We're going to force a couple to have 6 children. Good. That's 6 too many. Any questions? No? No? Okay, so now another notation is that we can label this as simple event number 1, label this as simple event number 2, label that as simple event number 3, and label that as simple event number 4. So there are 4 simple events that can happen in this situation. Good? Good? Okay, so you can either describe it this way, or you can define it as x equals to e sub 1, e sub 2, e sub 3, e sub 4. So sometimes it's convenient to actually write down the results, BB, BG, GB, and sometimes it's more convenient to use this kind of notation and then maybe go off to the side and describe what they mean, right? Particularly when there's patterns, when there's something where you can go, E1 is this, E2, and then dot, 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 because there's a pattern that's been established. It might make it nicer to write it that way. Or if you're going to be using this a lot, then it's nice to define what these things are separately so that you can just stick to this rather than having ugly long descriptions throughout the whole thing. So notation is heavy in statistics. It's important to know it so that you can understand what people are trying to tell you, or so that you can communicate to other people the ideas that you have, right? They're very complicated ideas, and so the notation has to be rather involved so that you can properly relate those ideas to people in a clear way. So unfortunately, the notation is kind of heavy. Okay, good. My intention is not to trip you up on, oh, you messed up, that's not how you do it, and gotcha. This isn't a gotcha kind of situation, but you have complicated ideas that you need to relate to me in a written form, and I need some way of getting that. So if you end up just writing it this way in a situation, I'm fine with it. If you prefer to write it this way, that's fine too. But we have to come up with some sort of common notation so that we can communicate and you can give me, you know, those complicated ideas in written form, and so hopefully, you know, we'll become clear on the notation. Okay, good. All right, so let's say that we are asked to find this, to find E as have one boy. So compound event, capital E, has been described or defined as the statement have one boy. Okay, what kinds of results would satisfy that condition, that a couple had one boy or have one boy? Does this one do it? Yeah, this one will do it. This one will do it. What about that one? Does not? Have one boy. So, did you have a boy? Yeah. You did. You had two, but one is in there. So, math, again, statistics is very specific. This didn't say have exactly one boy. It said have a boy. So have exactly one boy would be a slightly different situation. So this one would be satisfied by boy-boy, or boy-girl, or girl-boy, which can also be described as E1, or E2, or E3. On the other hand, if we had another event, let's say capital event, capital A, have exactly one boy, then that can only be described by boy, girl, girl, boy, which is E sub 2 or E sub 3. Any questions? No? Good? Questions? Good? Good? Okay, so those are events. Right, so there's our sample space. So we need some rules for probability. Two main rules we have to keep track of when we're dealing with probability. Rule number one is that all the probabilities have to be values between 0 and 1, inclusive of 0 or 1, right? That's their decimal representations. Or if you're going to write them as percentages, as probabilities, then they have to be a probability between 0 to 100%. Right? We cannot have anything that's negative percent, and we cannot have anything that's above 100%. I know we use that a lot in colloquial situations of give it 110%. That doesn't make sense in math. That's silly. You can't give 110%. There's only 100. 100 is all of it. You can't give more than all of it, right? Okay. So between 0 and 1 as a decimal representation, including the 0, including the 1. And then also the other thing is that if we take an experiment and we break it down into all its simple events, right? And then we find all the probabilities of each simple event, then the sum of those probabilities has to be equal to 100%. That's the other rule. Okay? The sum of the probabilities of the simple events, not the compound events, just the simple ones, have to add up to 100%. Okay, good. A little bit more notation. Capital P, this way, like if we write a capital P with like E sub 3 like this capital P with the parentheses like this is indicating that we want to find the probability of this event. Probability of simple event number 3. In this case, we were talking about a couple having 2 children. Simple event number 3 was the case of girl-boy, in that order, girl-boy. Right, so then we write down the probability of that. So let's say that the probability of that happening is 0.25%. Or 25%. Okay, so that's the notation that we would use for it. On the other hand, if we had, probability of getting event capital E is equal to 0.75% or 75%, then that's the notation we would get. On the other hand, capital N, like this, is used to identify the number of things in that event. So this is the probability of that event, where capital N is the number of outcomes in that event. So since this is a simple event, well then that's an easy answer. There's only one, right? On the other hand, in compound event E, how many outcomes were there in have one boy? There were 3 of them. Okay. So this is a probability. This is a number of outcomes in the event. Any questions? No? 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 Okay, so looking at the notation that they've given us for a sample space, S is equal to E sub 1, E sub 2, E sub 3, all the way out to E sub n. That's letting us know that in general, if we have n simple events in our sample space, then that would describe the entire sample space. And if we find the probability of each one of those events and add them together, they have to add up to 1. Okay. I think that should make some intuitive sense at this point. We'll see some examples in a second of why that makes more sense. Good. All right. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probability. So here's an example. Let's say we have a bag of peanut M&Ms, peanut M&M milk chocolate candies. The colors of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table to the right shows each color and the probability of drawing that color. So verify that this is a probability model. Okay, so first of all, in order for it to be a probability model, every possible outcome has to be described. So for instance, is it possible for you to pull out a candy and it's fuchsia? Do they have fuchsia in M&Ms? They don't have fuchsia. Do they have purple? They don't have purple. They only have those right there, right? So we've included all possible results out of the experiment of bringing out one candy and looking at the color. Good? Okay, so now we've listed all possible outcomes. Those are each simple events. Simple event number 1, it's a brown. Simple event number 2, it's a yellow. Simple event number 3, it's a red. Right? So we have all our simple events that make up our sample space. And we also have given to us the probability of each one. The likelihood that if I pick one candy out, that it's going to be orange. That if I pick one candy out, it's going to be blue. They're right there, and they're not equal, right? So for some reason, the company has chosen not to make them an equal proportion. I don't know why. Maybe they find that this is the particular color combination that people like most. Maybe people buy more candy with a certain color combination. I don't know what the reason is. But it looks like blue and orange are more likely, and brown and red are the rarest at 12% each. Okay, so in order for it to satisfy both conditions, each individual probability has to be a number between 0 and 1. Done. That's easy, right? They're all right there. On the other hand, also the sum of all of them has to add up to 1 or 100%. So we just add them all up, and yes, they all add up to 1. So this satisfies a probability distribution, probability model. Any questions on a probability model? No? No? So if an event is impossible, it's never going to happen, we label it as a 0. And if an event is for certain, it's definitely going to happen, then we say it's 100%. Anything close to 0 is highly unlikely of happening. The closer it is, the more unlikely it's going to happen. And the closer it is to 1, the more likely that it is going to happen, though we only reserve the 0 and the 1 for when you're absolutely certain, which in real life is pretty rare. There's only a few things that are absolutely for certain. Can everybody think of something that's absolutely for certain? Death. Yes, beautiful way to start our morning. Death. Yes, death is certain, right? Absolutely 100% sure that we are going to die at some point, all of us. So that's 100% sure. I would give that a 1. What's absolutely impossible? Not going to happen. Okay, you can go the opposite. I'm not going to die. I'm going to live forever. It's impossible. I'm going to live forever. Okay, all right. Anything else other than death? Okay, that's a great example. Change our eye color. At this juncture in time with our technology, I would absolutely give that a impossible. Not going to be able to do it. Are you certain that we are never ever going to be able to do that in the future? I don't know. It seems unlikely, but who knows? Maybe they invent some awesome pill, like 150 years from now, you can go to Walgreens and buy a pill, and like the next morning you wake up and your eye color is different. I don't know. It seems unlikely, but I wouldn't give it a 0 that in the future we're not going to be able to. It certainly is 0 today. Can't do that today. But maybe I would give it a very, very small number that maybe in the future we could do that. Right? So we like to reserve 0 and 1 for things where we are really, really certain on. And there's very few things that we can reserve certainty to. Right? Yeah. Men will never be able to give birth to a child. Yes. Is that one of those dumb movies where they do? I don't know. I think Schwarzenegger was in one of them. Oh, good. None of you are Schwarzenegger fans. I don't know what it was. But yes, in the movies they do that from time to time. It's silly. It's never going to happen. I think we can confidently say 0 chance today and 0 chance in the future, right? It doesn't seem likely that that's ever going to happen. Okay, men not being able to give birth, we're all going to die, and taxes, right? That's the other one. Death and taxes, the only things that you can count on. Okay, so unusual events are things that are low probability. They're close to 0. And what that is, well, by default, if nothing else is given, we consider 5% or lower to be unusual, unless it's otherwise stated. Sometimes we consider less than 1% to be unusual, sometimes even lower than that, right? So it depends on what we're talking about. So, for instance, if I worked at the quality control department at M&M's, and they told me that they want those probabilities to stay consistent, and they want those things to stay consistent with a certain threshold, maybe they would be okay with me saying there's a 5% chance that someone grabs a bag and it doesn't really fit the color combinations that you were looking for. It's not the end of the world. On the other hand, a 5% unusual, let's say I worked at quality control at Boeing airline, and there's a 5% chance that we messed up on something and the plane might crash. 5% is not that great, is it, at that point? So it depends on what you're talking about. Sometimes we want unusual to be really unusual. We want a 1 in 1,000 chance, 1 in 10,000 chance, right? Cars that drive themselves are coming soon, right? Yeah. The technology is almost there. The policies are, the bigger hurdle at this point, I think. Is it going to stop all accidents? No, there will be accidents. Okay, for sure. It's going to happen. Accidents happen. So, right now, if we have humans driving cars, let's say that there is about a 1 in 1,000 chance you might get into a car accident, a 1 in 10,000 chance you get in a car accident. The technology has to surpass that, right? It can't be equal to what humans can do, because we will completely attack the companies. We expect perfection. So they're aiming at a much higher threshold than that. They want to have a 1 in a million chance, a 1 in a billion chance, something incredibly rare, because if it's the same as what you have now, 1 in 1,000, say, I don't think people would trust the machine as much, right? Would you get into a machine and let it drive and just kick back and fall asleep if you knew that there was a 1 in 1,000 chance you might get in a car accident? I think you might be a little nervous, right? Even though that's what the odds are if you're driving yourself, right? Because things happen. Other people make mistakes. Tires blow out. Junk on the road, pothole. Things happen. But if you're going to trust your life to a machine, you expect that threshold to be much higher, which is what they're shooting for, and that's one of the reasons why It's still going to take a little while longer. They can drive now, but they haven't reached those thresholds yet, so it's still not at a place where they can release it completely. Plus, we have laws and insurance issues and all kinds of other stuff to deal with, but they will be coming soon. Anyway, how do we find those probabilities? In this class, there are three approaches that we're going to have to try and establish the probability of some event. The classical, the empirical, and the subjective methods. Okay? So first, let's look into classical. So the classical method of computing probabilities requires equally likely outcomes. That's really important to keep in mind. I'll refresh your memory of that in a second when we go through our example, but it's very important to keep that in mind. So an experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. Right? All the simple events have the same probability of occurring. Here is a more formal definition of classical probability. So if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E, noted as P of E, is P of E equals to the number of ways E can occur divided by the number of possible outcomes, which results in m over n. All right, let's refer back to this guy. So back when we were rolling one die, we rolled one die, that's our experiment. One six-sided die, it's fair, it's equal, all six sides have an equal chance of occurring. So there's our sample space. We can also write it this way, there's our sample space. And then we can also write it this way, so we're thinking about the different ways of writing it. So then we got into the events. A simple event would be E1, we roll a 1, E2, we roll a 2. Okay, those are the simple events. Here are some compound events. Compound event is that I rolled an even number. All right, it could have been a 2, a 4, or a 6. I rolled a perfect square. Well, that's either a 1 or a 4. Okay, so those are the compound events. So now let's look at the probability of those events. All right, so now let's look at probabilities. So let's say I have the probability of E1, which is the probability that we get simple event 1. We can also just write this as the probability that the die equals a 1, right, whichever makes more sense. And so according to our formal definition, this probability is the number of ways in which this can happen divided by the total number of possible outcomes. So this is going to be the number of ways to roll a 1 divided by the number, total number of outcomes. Okay, well that seems kind of silly. How many ways can you roll a 1? Well, there's only 1. And what is the total number of outcomes? Well, there are 6 of them. So in this case, the probability that we get a 1, the probability that event, simple event E sub 1 occurs is equal to 1 out of 6. Good? Questions, comments? Is that 0.1666, I think? Is that right? People with calculators? Stats people? Oh, good stats people? 1 out of 6? Alright, so there we go. So that's approximately 16.67%. Okay. On the other hand, now let's find the probability that we get an odd number. Probability that we roll an odd number. As far as notation, we can also define some capital letters. So like let's say we let B equal roll an odd number. So if we let capital B represent that, then we can also rewrite this as P of B. Okay? You don't have to do them both, it's just sometimes one makes more sense than the other. Or sometimes you want to just write down the whole thing, roll an odd number. Okay? Alright, so now this is going to be equal to the number of ways to roll and odd divided by the total number of outcomes. Okay, so the total number of ways to roll an odd number, well now we have different possibilities. We can either roll a 1, or a 3, or a 5. So I wrote them all down. Or, and then the total number of possible outcomes are 1, 2, 3, 4, 5, and 6. So I want the number of ways. I've actually written down the results, but I don't want the results, I want the number of ways. So now we can use our notation from before. Capital N represents the number of values in our event. So this is going to be N of capital B divided by N of capital S. And so finally we'd say that this is 3 out of 6, which is a half or 50%. Any questions about that? No? So think about the experiment, the sample space. This whole thing only works if each of these simple events are equally likely of occurring, and then you just count things. The event that I'm trying to find a probability for, how many ways can that occur? So you got to count those number of ways, and then divide it by the total number of simple events in our sample space. Good. Good. So another definition for this would involve this. P of E is equal to N of E over N of S. Or N of E is the number of outcomes in the event E, and N of S is equal to the number of outcomes in the sample space. Let's look at this example. Suppose a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, 2 green candies. Suppose that a candy is randomly selected. What is the probability that it is a yellow candy? Okay. So let's look at our sample space. The experiment is to draw one candy and take a look at its color, right? So the experiment is to select one M&M candy, select at random one M&M candy, and note the color. Okay, that's all we're doing. So what are the possible, what's our sample space going to be? Brown, yellow, red, orange, blue, and green. Okay? And what is our, so they wanted us to find out the probability that we get a yellow. So only one yellow. 1, 2, 3, 4, 5, 6 of them. So this is again 0.1666 or 16.67%. Something is wrong with what I'm doing. What's wrong with it? Lots of people are saying it. Yeah, it doesn't make any sense. Well, first of all, because I didn't spell brown right. That's one reason it doesn't make sense. But it doesn't make any sense because these things are not equally likely of occurring, right? There's a lot more of one color than another color, so it's not true to think that getting a blue one is equally likely as getting a brown one, right? We have a lot more brown ones than we have blue ones. So this is not an adequate description of our sample space in this case. Now, if I only had one candy of each color, here's one brown one, here's one yellow, here's one red one, here's one blue, here's one orange, here's one green. We shake it all up, we reach in there and randomly grab one. now this would be a perfectly good situation. But because we have a bunch of them, this doesn't work. This is not true, again, because these are not equally likely of occurring the way I've written them down. So we have to keep track of the fact that there are different ones. So now one thing you could do, just for the sake of notation, is you can say that there were 9 brown ones, there were 6 yellow ones, there were 7 red ones, there were 4 orange, and then there were 2 blue and 2 green. So this is sort of a shortcut of my notation that I want to do. You could also say, you can put them down as brown, 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 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there was 1, 2, 3, 4, 5, 6, 6. Then 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, and brown and blue. So I can't use B. I don't know. Let's use E. E is not a good one to use. How about L? L, L, L. Oh, 2 L's. And then G for green. Okay. So I need to subscript them so I know which one is which one is which. So let's say they all have little numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4. 1, 2, 1, 2. Okay. Now we have a better description of our sample space. These are all the possible things. Now, is it really necessary to write it all down? No. I think we would have been perfectly okay with the understanding that we have this sort of situation. Good? Okay. So now when they say find the probability that I pick a yellow, well, they didn't say which yellow. They didn't say yellow number 2 or yellow number 4. If that was what they were saying, if all the candies did have these numbers in them, and they said, what's the probability of getting yellow number 5? Well, there's only one yellow number 5. But they just said, what's the probability of being yellow? Okay, well now there are 6 ways to getting that, right? So this is going to be equal to the number of ways of getting a yellow divided by the number of values in my sample space, capital S. Capital S is always a sample space. And so now I can say that there were 6 ways to get my yellow, divided by the total number, and there's 30 of them. So 1 out of 5, or 20%. Good? Questions? Comments? Issues? No? So we can do classical because now, the way I've written them, now they're all equally likely, right? The odds of getting orange number 1 are the same as the odds of getting yellow number 4, right? That individual unique one. But by color, they're not equally likely. Does that make sense? Good? No? Good? Good, good? Okay. What's the probability of getting a blue one then? Number of ways of getting a blue divided by the number of values in our sample space, which is equal to blues, there were 9 of them, divided by 30. Oh, sorry, yes, 2 out of 30, which is 1 out of 15, which is 0.06666666. So so we can write it as 6.667%. We're good with 4. Any questions? No? So which one's more likely of occurring? Yellow one is more likely of occurring. If I reach in there and I randomly grab one candy, it's more likely that it's going to be a yellow one versus a blue one. Right? There's more yellow ones in there. And the most likely one is going to be a brown, because there's more brown ones in there. Good? Okay. So that covers that. So the other method that we're going to employ to figure out probabilities is called the empirical method. So the probability of event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So relative frequency, or the relative, P of E is equal to the relative frequency of E. Okay, so it's equal to the frequency of E divided by the number of trials of the experiment. So this goes back to a situation where we know what the outcomes are, but those outcomes are not necessarily equally likely of occurring. So, for instance, remember the movie Rat Race? Remember there was a bunch of really wealthy people, and they were like addicted to gambling, but they would gamble on the weirdest things. Yes, you guys remember that? Okay, so they would do things like, you know, they would wager $1 million to see, you know, which person can hang off a ledge the longest before they let go, or, you know, weird things that they would bet on. So how do you find those probabilities? How do you figure out what those likelihoods are? Well, one way to do that is to repeat the experiment. Do it over and over and over, and keep track of your results until you get it. For instance, if I have this little box right here, if I toss it in the air and let it land on the floor, it can land this way with this face up, or it can land this way with this thing up, right? Or it can land on its side, right? Or on its other side, or on this side, right? It can't land on this side because of physics, right? It's got this thing on here. So there is one way, there's another way, there's this way, there's this way. So how do I do that? How do I figure out the probability of each? So you can't do a situation where you write down all possible outcomes and they're all equally likely, because they're not. It feels like, to me, that landing this way is probably going to be the rarest thing, right? So what if it was a Las Vegas game, and you bet $1, if it lands this way, you win $100, and if it doesn't, you lose. Is that a good bet? What do you think? You wouldn't bet that? What if it was you bet $1, and if it lands this way, you win let's say $1 million? Is it a safe bet? What are the odds that if I throw it in the air, it's going to land? No, not that time. Keep tossing it up in the air. Oh, no, not that time. So, what are the odds that it's going to land exactly facing up like that? That's what we want to find out. Is it a good bet? $1, and if it does land that way, you win $1 million. You would do it? Would you sit there with a stack of $1,000 and you're like one at a time? $1, $1, $1. I'm gonna win $1, $1, $1. No? Who knows? Maybe in those 1,000 times, maybe you win. Maybe, oh my God, you're an evil genius. Look at that. You became a millionaire. No? Okay, so how do we find that out? Well, one way to do it is the empirical method, which is just to do it. You just flip it over and over and over. You flip it over and over and over. You keep track of your results, and then you keep track of the thing you're looking for, event E. In this case, I was talking about it landing this way. So you keep track of it, and then you divide the frequency of times, the number of times that you observed the event that you were looking for, divided by the number of trials, and that gives you your best guess. Now, this isn't exactly the probability. It's just that it approaches the probability as we do this a large number of times. Good? Questions? So this is similar to the coin app that we looked at a minute ago.
Okay, so let's take a look at this coin flipping app one more time, but this time through the lens of empirical probability. So let's say that you are given a coin, and maybe perhaps you begin with the intuitive thinking that it's a fair coin and that there's a 50% chance that you flip it and you get a heads, and there's a 50% chance that you flip it and you get a tails, except that this is a trick coin. It's designed not to be a fair coin, it's an unfair coin, and it's designed to give a probability of heads of 80%, so a lot more heads than tails. But you don't know this. You don't know what the real probability is. We call this the theoretical probability, the true probability of the coin landing on heads. It's 80%. But if you don't know that, then you begin examining this coin by doing the empirical method, which means you begin flipping and keeping track of your results. So you flip it once, and you get a heads. So as of right now, the empirical result is 1 out of 1, so there's a 100% chance of getting a heads when you flip this coin. The proportion is 1 over 1, so the probability is 100%. So if we were just going to use this as our best guess for what the probability of rolling a heads is, or flipping a heads out of this coin is, we would say 100%. But it is a very low chance that you're accurate because you've only flipped it once. Remember, the law of large numbers tells us that we have to do this many, many times because we know that eventually the cumulative proportion is going to approximate the true probability of landing on heads. So we do it again. Oh, we got heads again. So that's 2 out of 2. So right now we still think it's 100%. Do it again. Do it again. Finally we got a tails. So at this point we flipped it 5 times, and 4 out of those 5 times resulted in 80%. And we know that that's the real answer. So one might argue, let's just stop there. We got to the real answer. But remember, we're pretending we don't know the real answer. So you just won't know to stop there because you don't know what the real answer is. So you're just going to keep flipping away, flipping away. So with 12 tosses, you have 10 heads and 2 tails. So right now, your running proportion is 10 out of 12, or 83%. If you stopped there, your very best guess would be, based on these 12, your empirical probability would be 83%. So 12 is still not a very big number, so you're not very confident about your guess, but your best guess as of now, your empirical result would be 83%. So by the law of large numbers, we know that we have to throw in large number of tosses, and as this total number of tosses becomes very, very large, this blue line will dance above and below the green one, but get infinitely close to it. So let's see what happens there. So if I flip it 1,000 times, now I have 1,012 flips. The blue line went below, looks like it stayed below for a while, then it went above a little bit, then went down below and up and below and so on and so forth. And after 1,012 tosses, 806 resulted in heads for a proportion of 0.7964, or 79.64%. So as the number of tosses increased, it got closer and closer to the real one. So if we didn't know that the real one was 80, this would be our empirical probability right now with 1,012 tosses. Now if we flipped it another 1,000 times, my empirical probability would be 1610 divided by 1012, which would give me a proportion of 0.8002, or 80.02%. Very close to the real one. So if I didn't know what the real one was, this would be my empirical probability, right? So the key about empirical probabilities is that you never really know when you're quote-unquote done or what the answer is, because you don't know what the answer is, and all you can do is just rely on the law of large numbers. And the bigger that total it is, the more I flip the coin, the more and more confident I am that my empirical probability is a really good approximation of the theoretical probability, the real probability. In this case, the real probability of this coin is 80%, and after 31, 32, 33, 35,000, 12 times, I'm really close to 80%. I'm ready to be very, very confident that this is a very good approximation to the real probability of getting a heads in this coin toss. Okay, so that's empirical probability. It's an approximation to the real probability based on experiments. You repeat the trials over and over, many, many times, as much as you can, and you use those results to give a good estimation of what that true probability is.
So, the frequency V divided by the number of trials of the experiment. Here's an example. Pass the pigs. Who's heard of Pass the Pigs? No? 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 So Pass the Pigs is a Milton Bradley game in which pigs are used as dice. These little pigs are used as dice. Points are earned based on the way the pigs land when you roll them. So there are 6 possible outcomes when one pig is tossed. So let's pause there for a second. Here's what they look like.
This is a serious game of Pass the Pigs. Keep tossing the pigs for points.
Razorback.
If you dare.
Yeah. Oinker.
You blew it.
A Dalton Snouter.
Get past the pigs. It's serious fun.
Right, these little plastic pig things, and they can land in different ways. They can either land like the one on the left there, all 4 feet, or they can land like the one on the right that's like leaning forward and touching on its nose. Or it could be leaning forward and touching on the nose and the ear, or there's standing again. All right, so there's different ways in which they can land. There are a total of 6 different ways in which it can land. It can land on its side, and see how one of them has a dot. See the side with a dot? That's the side with a dot. If it lands on its side with a dot, or if it lands on its side without the dot, that's one possibility. Or it can land on all 4 feet, or it can land on its leaning forward on its nose, or it can land leaning forward on its nose and its ear. So there are 6 different positions, and here they are. So 52 students rolled the one single pig 3,939 times and recorded how often the various results occurred. So the numbers are tabulated here on this table. It landed on the side with no dot 1,344 times. It landed on the side with a dot 1,294 times. It landed razorback, that's on its back, just all 4 feet in the air, 767 times. It landed trotter, which is on all 4 feet, like normal walking, 365 times. Snouter is when you lean forward just touching the nose. And it landed that way 137 times. And it landed forward touching the nose and an ear 32 times. So those are the results. So based on that, we can get a pretty good feel for what the probability of these positions is, right? So obviously the leaning jawler is the most rare, probably the one that's worth the most number of points. And the probability can be approximated by, first of all, well, we already know the total number of times it was rolled was 3,939, but we take the 32 and divide it by that. Right? So for the first one, the probability that it lands on its side with no dot, we would take the 1,344 divided by 39, and we get 0.341. There seems to be approximately a 34.1 chance, based on my empirical information, that if you roll one pig, it's going to land on the side with no dot. And that's how you find the other ones as well. The frequency of how often you saw that happen divided by the total number of trials. Okay? So as we saw before, the law of large numbers, as we do it a large number of times, the results are going to begin to approach their real probability. So the real probability might just be, for example, exactly 34% for the side with no dot. We don't really know what the real answer is. Or maybe the real answer is 34.5. I don't know. Maybe if I kept doing this more often, I would see that they're a little bit different. If another group of people rolled this little pig 3,939 times, they might get slightly different results. But they're not going to be that much different, right? They're going to be somewhat close, and they're going to get probabilities that are fairly close to this, and all of those will be fairly close to the real theoretical probabilities which are out there, right? I don't know what the real absolute theoretical probability is. All I have is a pretty good approximation. And the bigger the samples, the number of trials that I run, the bigger that number is, the more confident I am in my results. If instead of 3,900 times, I did this 1 million times, I would be even more confident that these are really close to what they should be. Any questions? No? You guys are all ready to go play? No? Yes? No? Okay. So the last one we want to talk about is subjective probabilities. That one's the easiest one. Subjective probability means that we leave it up to experts. So, for instance, who's a good, I don't know, professional fighter of any kind of professional fighting? Anybody know? Mayweather. Oh yeah, Mayweather. Alright, so here's a question. Would you agree Maybe they're having one of these Rocky kind of things where they're gonna like randomly pick someone that's unknown to fight the professional. Would you fight the professional? 1 round, national TV, you versus Mayweather. You get paid $1,000. You do it? It's just 3 minutes. How much damage could the man do in 3 minutes? A lot of damage. All right, all right. Would you do it for $10,000? Would you do it for $1 million? 3 minutes. Health, your own health fails afterwards, so whatever damage he does, you got to cover out of your $1 million. Would you do it? 5 million. So it seems like most people have a price. At some point, you're like, all right, I guess I'll just run for 3 minutes and see if he doesn't catch me, or just curl down in fetal position and cry until the 3 minutes are done. I don't know. You can't tap out though. He's going to work on you for 3 minutes, no matter what happens. Did you do it? Okay. So, is it possible you would win? There's a possibility, right? Could be. Maybe he trips on his shoelace and falls down and knocks himself out. That could happen. Maybe you're kind of like crying and just sort of swinging and you get lucky, I guess. I don't know. Something could happen. I don't know. There is a chance. So a very, very small chance, right? So the probability that you win. So can we do this? The sample space is either you win or, more likely, you lose. So the probability that you win is equal to 1 out of 2 or 50%. Either you win or he wins, so it's 50%. Is that the way it works? No, right? That's not the way it works. It makes intuitive sense that that's not the way it works. There's no way you got a 50% chance of beating Mayweather. No way. So what's the problem? This is the sample space, right? Either you win or you lose. But these two are not, they're not equally likely. So how do we figure out that? Well, we saw that classical doesn't work, right? Because they're not equally likely. Can we do empirical? What would that mean? That would mean that you just do it over and over, right? Fight him one time, see if you win or lose. Fight him again, see if you win or lose. Fight him again, see if you win or lose. Do it over and over, and after you've fought him about, 10,000 times, maybe we figure out that one of those times he lost for some reason. So you go, okay, the odds of winning are 1 in 10,000. Okay, obviously, we really can't do that, right? You wouldn't live through 10,000 fights, for one. We don't have the time. He gets paid like $100 million a fight, so there's no way he's going to spend all that time. Right? It just doesn't make any sense. There are many cases where we cannot employ classical and we cannot employ empirical. If we could, we would do a simulation. We could do that, get a computer simulation, put in all those stats into one thing, let the computer repeat it over and over and over. In some cases, that makes sense. Would it make sense in this case? Can we do a computer simulation where we put in all the stuff, your height, your weight, and it's hard, right? Because you really can't put ability in there. And how do you determine that, right? So in some cases, we do simulation to repeat that over and over again until we get a pretty good idea. We do that a lot with like airplane manufacturing now. We can put simulations to like weather and rain, weather, and we can put a new plane design and kind of have an idea of how it's going to interact in that environment. And we just do simulations over and over. Or crashing a car, we can put a digital image of a particular vehicle we're thinking about, and we can put it through a crash and simulate what would happen in the cabin and how things move and the airbags. And so we could do that as well. But in this case, I don't think it would make sense. So the only thing we have left is this last thing, which is subjective probability. Subjective probability means that we leave it up to the experts. The experts are going to decide. They have, they study the various, all the variables involved, reach and weight and agility and all kinds of stuff that goes into it. And an expert would give us what are the odds that somebody would win or lose. So this fight or any kind of sport thing usually is a subjective probability, right? What are the odds that the new Los Angeles Rams are going to win the Super Bowl this year? This next coming season, at least. Okay, we don't like to use zeros around here, but it's probably pretty close to 0. So, who's really going to come up with a number? an expert, right? They're going to look at the players and the coaches and all kinds of variables. And as the season begins to, unravel, then all kinds of stuff comes in. You got injuries and you got substitutions and you got fights between people and all these things come into play. And you rely on these experts to know what they're talking about, and they're the ones that give us the best possible probability of something occurring. Okay. Now, what does that mean in our class? Well, we can't do that. We're not experts. So when we run into an exercise that involves this, all you have to do is identify that this is a case where subjective probability is applied. Right? This is a leave it to the experts kind of situation. Any questions? Okay, so classical, we're counting things. We're counting the total number of simple outcomes. If the probability of each of those outcomes is equally likely of occurring, then we can use classical. So we're going to count how many of those simple events constitute the compound event they're asking us to find out. So we got to count the numerator divided by the count the denominator. Empirical means that we're going to repeat an experiment over and over and over and over, and we're going to keep track of the results we're getting, and we're going to keep track of how often we get a particular event that we're looking for, and we're going to divide them. And then subjective, which means we leave it to the experts.